In recent years, large language models are in charge of remarkable advances in AI, with models such as GPT-3 and 4, which are closed source, and with open source models such as Llama 2 and 3, and many more. However, as we moved forward, these models got larger and larger, and it became important to find ways to improve their efficiency. One known method that has been adopted with impressive success is called Mixture-of-Experts, or MoE in short, which allows to increase models' capacity without a proportional increase in computational cost. The idea is the different parts of the model, which are the experts, learn to handle certain types of inputs, and the model learns when to use each expert. For a given input, only a portion of the experts are used, which makes this model more compute efficient. But let me ask you a question. What do you think was invented first, MoE or transformers? Transformers were invented in the famous Attention is All You Need paper from Google at June 2017, while Mixture-of-Experts Layer, which is very similar to what is used in LLMs today, was actually invented earlier in the same year, also by Google, in a paper titled Outrageously Large Neural Networks, the Sparsely-Gated Mixture-of-Experts Layer, with authors including none other than Geoffrey Hinton, also known as the godfather of AI. In this video we go back to this extremely important paper to understand how Mixture-of-Experts work. Let's get straight to the point. The paper introduced the Sparse Mixture-of-Experts Layer. The idea with Mixture-of-Experts is that instead of having one large model that handles all of the input space, we divide the problem such that different inputs are handled by different segments of the model. These different model segments are called the experts. What does it mean? We have a router or gating component and an experts component, where the expert component is comprised of multiple distinct experts, each with its own weights, and given input tokens such as the A tokens on the left. Each token passes via the router, and the router decides which expert should handle this token, and routes the token to be processed by that expert. More commonly, the router chooses more than one expert for each token, so in this example we choose 2 experts out of 4, and then the chosen experts yield outputs which we combine together. These experts can be smaller than if we would use one large model to process all tokens, and they can run in parallel, and not all of them need to run for each input, so this is why the computational cost is reduced. This flow is repeated for each input token, so the second token also passes via the router, and the router can choose different experts to activate. For example, here it chose the top expert, same as before, and the third expert instead of the last, and it goes on for each input token. For the input prompt, the tokens are handled together, and we do not do this one after the other as shown in this example. For the router, various techniques to implement the routing function were introduced over time since the paper was published, which we won't dive into here. In this example, we also present a single layer, while there are usually more than one, so the outputs from this layer are propagated to the next layer in the model. Before moving on, if you're getting value from this content, then please consider subscribing to the channel and hit the like button to help this channel grow. We also send 1-minute read summaries by mail about the papers we review here. You may find a link to join in the description of this video. Let's now also review a figure from the paper which presents the MoE layer. Since this is from before the Transformers era, the model used here is a recurrent language model. At the bottom we can see the input to the MoE layer, which is provided from the previous layer. The input first passes via the gating network, which decides which experts should process the input. We see that there are n experts, and the 2 of them were chosen. Another role of the gating network is not only to decide which experts to use, but also to determine the weight of each expert output. Finally, we can see that the outputs from the chosen expert are combined together based on the gating network output, which gives us a weighted sum of the experts' outputs, which is forwarded to the next model layer. The different MoE layers, the gating components and the experts are all trained together as part of the same model. Thank you for watching and stay tuned for more reviews of AI papers.